Today we're going to be talking about the imaginary unit I. And I is a number. I represents the radical of -1. So this is I. So anytime that we see the radical of -1, we're going to replace it with I. Okay. This is known as a complex number. So here's our little definition of a complex number. And it says this. It says if A and B are real numbers, so numbers that I can physically count to, then the number A plus BI is a complex number. And the reason why it's a complex number is it's because it has two parts. Okay, so A plus BI. Okay, the first part is the A, and this is what's known as the real part. Right, so I can physically count to that. And the BI is the imaginary part. Okay, and together they make a complex number. This is also known as standard form. So anytime I ask you guys to write your answer, we want to make sure that we write it in standard form. So what can I do with imaginary numbers? Well, the first thing I can do is I can add them and I can subtract them. So this is known as the sum and difference of complex numbers. Okay, so for sum, all this means is that we're adding. So A plus BI, so we have one value, and we're going to add it with the C plus DI, so we just change the letters. So essentially what you're doing is you're adding your real components together. So you'd be adding the A plus C together, and then you'd be adding the imaginary components, B plus DI. Okay, difference just means that we're going to subtract. And so again, A plus BI, and then this time minus, so C plus DI. And so you'll take your values and you'll subtract the A and the C together, and you'll subtract the C and the D together. Now notice that there is an addition sign because we don't actually know what number we plug in for C and D, if this is actually going to turn out to be a positive or a negative number. So let's go ahead and do an example. Okay, so if I have the complex number, so we'll call this number 1, 4 minus 3i, and then I'm going to add that with 3 minus 5i. So again, I'm just going to be combining values. So I'm combining my real components. So I'm saying 4 plus 3. So if I add 4 and 3 together, I'm going to get 7. And then I'm going to add the -3 and the -5 together. So that's going to give me -8. So I'm going to say minus 8i. I can also say plus -8i. They both mean exactly the same. What happens if I have something like this? The radical of -9 minus -5 minus the square root of -25. So I made this a little bit more complicated. First thing we want to do is we want to take the radical of -9, and again, that is like saying the radical of 9 times the radical of -1. So the radical of 9 we can simplify to 3, and this simplifies to I. So we're pulling out the i's, but don't worry, it doesn't hurt because they're imaginary. So we get 3i, and then we'll say minus, and this will be -5. And we'll do the same thing over here. So this will be minus 5i. Right? I'll distribute the negative, so this becomes -3i. And then I can say plus 5 plus 5i, and then combine my like terms, 5 plus 8i. So again, another different way to solve for this. Okay. what else can I do with imaginary numbers? I can also multiply them. So in order to multiply with our imaginary numbers, we need to know a pattern. So multiplying our complex numbers. Okay, so as long as we know that the radical of -1 is equal to I, we also know that -1 is I squared. So we're going to start a pattern. We're going to say I to the power of 1, I squared, I cubed, I to the power of 4, and we'll go a couple more. Okay, so the first one is I to the power of 1. We're just going to call that I. Okay, so we're not going to write it with any radicals because we have to remember we're trying to always write things into the standard form, and notice that the standard form does include an I, but it doesn't have exponents. So all of these have exponents. So let's see what happens. So I squared, right, is just -1, and that's based on our definition. So what about I cubed, right? Well, I cubed, we use our exponent rules. That's like saying I squared and I to the power of 1, right? So that would give me 2 plus 1, which gives me 3. So I know I squared is -1, and I know I to the power of 1 is just I. So this means that this guy is -I. I to the power of 4, that could be I squared and I squared. So that's the same thing as saying -1 times -1, and I get a +1. Okay, I'm going to continue this pattern, and what I'm going to notice, if I do I to the power of 5, and again, I can pick any numbers, so let's do I cubed and squared. So this will give me -I times -1. The two negatives are going to cancel out. Notice I'm right back to I, which is the same, which was the same one as I to the power of 1. So let's see what happens with I to the power of 6. So that could be 3 and 3. So this becomes -I times -I. Well, the two negatives cancel out, leaving me with I squared. I squared is -1. I to the power of 7, that's like maybe 4 and 3. So 4 is just 1. I cubed is just -I. So I get -I down here. And then I to the power of 8, again, maybe 4 and 4. If I add those two numbers together, I can also add more than just two numbers, but I'm choosing just two numbers. So it's just 1 and 1, so I get 1. So notice that the pattern repeats after 4. So if we can remember this pattern right here, okay, then we know that we are good to go. And how we can remember this is that when I win the lottery, right, I'm going to jump up and down, right, scream from the rooftops that I won, I won. Negatives are in the middle. So what does that kind of look like? It looks like this. So I won, right, I won. Actually, let me spell it out like this, right? Well, I'll write it out in words that I won. I won, I won. Negatives are in the middle, right? That's what I just screamed from the rooftops. And in reality, what I just wrote is I just wrote I, and then the number 1, I, and the number 1. My negatives are in the middle, right? So again, it's kind of a little play on words. So if we actually know that this pattern repeats every 4, so pattern repeats every 4, okay, what we can actually do is we can use that information to figure out higher degrees, right? So I to the power of 32, right? So what I'm going to do is I want to look at my exponent. My exponent is 32, and I want to see how many times 4 goes into 32. And I'm looking at the remainder. So look at remainder, okay? And things are going to happen. You're either going to get a remainder of 1, 2, 3, or none. The none is like the I to the power of 4. The 3 will be like I to the power 3, 2 will be I squared, and then 1's like the 1. So 4 does go into 32, and it goes in 8 times. Again, it doesn't really matter, but what we're looking at is the 0. So I know that this is equivalent to I to the power 4, which means that this answer is just 1. Now, we could go the long way, and I can say, okay, I to the power 1 is I squared was negative 1. Oops, write it out like that, negative 1. I cubed is negative I to the power 4 is 1. So I could go 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and I can continue this pattern until I get to 32. But that seems excessive and long. So if we can kind of remember just to divide everything by 4 and look at the remainder, we have an idea of what is happening. Okay, and we can pick any number. So let's go larger. Let's go to I to the power of 333, right? So again, I know 4 is not going to go evenly into this number. But 4 goes into 33 8 times, right? Oops, that's a 32. And I'm going to have 13 remaining. And 4 goes into 13 3 times with 1 remaining. So this is equivalent to I to the power of 1, which means this guy is just I. Right? And again, I can do it for anything. Let's go I to the power of 70. Let's just go 70. Yeah. So 4 goes into 70. So 4 goes into 7 one time. The remainder of 3. Bring down the 0. 4 goes into 30 7 times with 2 as a remainder. So this is equivalent to I squared. So that means I squared is negative 1. And the reason why this is important, right? I said we can add and we can subtract and we can multiply our numbers. So what happens if I give you a problem that looks like this? So negative 4 times the square root of negative 16. Make a note. Do not multiply the radicals together. Change to a complex number first. Okay, so what am I going to get? So the radical of 4 is really 2i. The radical of 16, right, is really 4i. Multiply 2 and 4 together, I'm going to get 8i squared. Again, I'm trying to write this in a complex number, a plus bi, and I have an I squared. So I need to replace the I squared with the negative 1. So this means that this answer is negative 8. Okay. Now, we want to be careful. Why did I say not to multiply it? Because you're going to get a very different answer. If you did this is what I don't want you to do. If you tried to multiply these together, okay, and you multiply negative 4 times negative 16, the negatives are going to cancel each other out, right? And it's going to leave you with a positive 64. You no longer have an imaginary unit. And now notice that your number is 8. Again, complex numbers do not work the same as just regular old numbers, right? So we do not do this. Okay. Let's try another multiplying. All right. So what happens if I have a binomial, right? Your complex number, so it almost looks like a binomial, times another one, right? Again, I like to set up my area model to visualize that multiplication. So 5 minus I, 7 plus 2I, so 35, negative 7I, 10I squared, negative 2I squared. So I'm going to get 35 plus 3I minus 2I squared. Again, it looks like a trinomial, but I always want to write it in my standard form. So I'm going to replace the I squared. So 35 plus 3I minus 2 times negative 1. That's going to give me a positive 2. I'll combine those values together. So 37 plus 3I. Okay. With imaginary numbers, we also have what's known as conjugates. So when we have complex conjugates, so complex conjugates, these are going to help us um, multiply and find our zeros because irrational numbers and imaginary numbers always come in pairs. So think of conjugates almost like pairs, right? So here's our complex number, and then here's your conjugate. And I'll put a couple up here. So we'll do 3 plus 2i, 4 minus 7i, and then I'm going to switch it up on this one, 2i minus 3. So when we're dealing with these complex conjugates, right? So I have a plus bi. The conjugate, so here's our original. Our conjugate is going to have the same real number and then the opposite of the imaginary part, right? So same real and opposite imaginary. So knowing that, if I look at my list, right, I have 3 plus 2i, and now I have 3 minus 2i. 4 minus 7i becomes 4 plus 7i. Now this one's tricky. I wrote it in a different form, but the 2i is the imaginary component, so it'd be actually negative 2i minus 3. Now, why are conjugates so important, right? Hopefully what you recognize is they're kind of like your difference of squares, right? Whenever if you had x squared minus 4, this would turn out to be x minus 2x plus 2. This is also an example of a conjugate. This is a complex conjugate, but this is also an example of a conjugate because the second term is the opposite, okay? So when you multiply these together, you kind of lose your middle term. And that's kind of what's going to happen when you multiply these together. So 3 plus 2i, 3 minus 2i. So notice what's going to happen. Your imaginary component is actually going to disappear. So 3 times 3 is going to give me 9 minus 6i plus 6i minus 4i squared. So I get 9 minus 4i squared, again, similar to difference of squares. But now notice that the I squared is really negative 1, which actually turns out to be 9 plus 4, which gives you 13. So the great thing about complex conjugates is that when you multiply them together, the imaginary component disappears, and you'll be able to just get a number. And why is this so important? Well, we've added, we've subtracted, and we've multiplied. The only other thing that we have not done is divide. So our last example, right, would be something like this. So we'll say 3 plus 4i all over 1 minus 2i. And I want us to write this in standard form. And again, a plus bi. Well, here's our problem. We have i's in the denominator, and I don't want to have an I in the denominator. So what do I do? Well, I'm going to multiply by the conjugate. So I'm going to rewrite this problem out. 1 minus 2i, and I'm going to multiply by the conjugate. 1 plus 2i. And as long as I multiply top and bottom by the same value, right, it's a fraction of 1, I'm not changing what this fraction is equivalent to. So again, 3 times 1 will give me 3. This will give me 6i plus 4i plus 8i squared. The denominator will be 1 minus 2i plus 2i minus 4i squared. Combining like terms, so 3 plus 10i plus 8i squared all over 1 minus 4i squared. And again, I can't just cross off the I squareds. This is a trinomial because it has 3 terms, and this is a binomial, right? It has 2 terms. So I, again, need to simplify it. So this becomes 3 plus 10i plus 8 times negative 1. over 1 minus 4 times negative 1. So essentially 3 plus 10i minus 8 all over 4, 1 plus 4, I should say. Combine like terms. So the 3 and the 8 gives me negative 5 plus 10i all over